Okay, so we are going to move on to chapter 8. Okay, chapter 7 was exponential properties and radicals. Now we're going to go into exponential functions, which means your exponent is now what's missing. Okay, so today we're going to look at the graphs. Okay, let's look at just the graphs first. So let's compare what a line and what an exponential look like compared to each other. So notice here it's 2 times x for linear. Exponential, it's 2 raised to x. Okay, so let's do 2 times x first. So these are all my x's. If I plug those in, so if I plug in -2, what is 2 times -2? What is it? -4. Okay, so that's a point on my graph. My x is -2. Remember, these are x's. These are your y's. Okay, my x is -2. My y is -4. All right, if I plug in -1, what is 2 times -1? -2. So my x is -1. My y is -2. All right, next, plug in 0. What is 2 times 0? 0. What fancy point is this called? The origin. Nice. Plug in the number 1. What's 2 times 1? 2. So x is 1. Oh, there you go. 2 times 2? 4. And then we have 6. Yes. Good. Okay. So when I have a linear function, what does the actual graph look like? It looks like a straight line. Absolutely. Okay. And it's increasing. Is it increasing at different paces, at the same pace? Okay, well, let's think about it. From -4 to -2, what happened? It went up 2, right? How about -2 to 0? From 0 to 2, 2 to 4, 4 to 6. So would you say it has a constant rate? It's increasing at a constant rate. Okay? So linear functions they have a constant rate. It's the exact same jump every single time. Okay? So those are linear functions. You know these. You do. I promise. Now, Reese. Thank you. Okay, now let's look at exponential. So now my x is being an exponent. So when I plug in -2, okay, I'm looking at 2 raised to the -2 power. Okay, 2 raised to the -1 power. I'm actually not going to start from the beginning. I'm going to start right in the middle. What is anything raised to the power of 0? Ooh. It was on that. It is 1. Good. It was on that graphic organizer at the very bottom. Right? That is 2 raised to the power of 0. Okay? So how about when I plug in 1? 2 raised to the power of 1 is, there you go. 2 squared is, yep. 2 cubes. 8. 2 times 2 times 2. You're multiplying it to itself 3 different times. All right, now throw back to our negative exponents. So 2 to the power of 1 was 2, right? But 2 to the -1 power is 1/2. What? It flips. Remember, a negative exponent means it drops. Okay. Okay. So that's my negative exponent rule. Okay. The next one's going to be 1/4. Yeah, 2 to the -2 power. It's 4, but it's flipped. It's 1/4. Yes. Okay. So let's just look at what this graph is going to do for us. All right. So we have -2 and a y value of 1/4, so it's very close. And then we have 1/2, 0, 1. X is 1, y is 2. X is 2, y is 4. X is 3, y is 8. So it starts really low, and then it like jumps up. How do we plot points? How do you plot points? So you do the X value first and then the Y. You just make it real close. If this block is 2, halfway up is 1, right? Half of that is half. Half of that is 1/4. Just make it real close. Yep, use your best judgment. Okay. Is this a line? No, what do you see happening?
I see it turning into a curve.
It turns into a curve, yes. So exponentials are going to be curves, okay? And is it increasing by the same amount each time?
No. We don't want to hear that.
Am I adding the same number like last time? Like little steps? No, if you ignore the fractions right now, that's like what, +1, +2, +4? So it's not the same thing each time. So we're not adding the same. We are doing what instead? Not adding. We are multiplying. What's 1 times 2? 2. 2 times 2. 4. 4 times 2. 8. So that's what's going on with exponentials. Instead of adding, now we're multiplying. Okay? So each time we increase our y value, we are actually multiplying by the same number. And in this case, that is 2. So this is called a constant ratio. This is called a constant ratio when you're multiplying. Mm-hmm. Okay. So we see how the graph looks different. Okay, it curves. This one never even crossed the x-axis. It just stayed there the whole time. Okay, let's look more into our functions and see what each piece is giving me. Okay, so when we write functions, exponential functions, they're in the form y equals a times b raised to the power of x. Okay, in this form, exponential functions have a variable as an exponent. That's the piece that's missing. Okay, we don't know our exponent. Okay, and 2 things can happen. It's either going to grow or decay rapidly. Okay, they're going to either jump up or they're going to fall down real fast. All right, and when they're written as a times b to the x, that a value is going to be our initial value, or where we start, which is the same thing as my y-intercept in my graph. Okay, so it is the initial value. So when we get to our word scenarios later, it's going to show where we start. A lot of this has to do with money. So it's like the money you start off with. Okay. In my graph, it's my y-intercept. Because that's where we start my graph. Okay, it cannot equal 0. Then the whole thing is 0. It doesn't matter anymore. Okay. The b, that number that is actually attached to our exponent. Okay. This is going to be our growth or decay rate. So it actually shows how quick or how slow, possibly, we are increasing or decreasing. Okay? It will be greater than 0. We're not going to mess with negatives right now. Okay? So we are not going to be doing any flipping or reflecting. Okay? That b value by itself, if it is going to be bigger than 1, then it is growing. 1 kind of represents like 100%. So if we're more than 1, we're actually increasing our value. Okay? And then if we are less than 1, it's a decay function. That means we're actually losing value. Okay? So if it's like, I don't know, 0.95, you're losing 5%, right? It's not all moving forward. Put it inside your bag, not resting against your bag. Thank you. Okay? So that rate shows you how much of your original item is moving forward. So 1 represents 100%. That's the original thing. More than 1 means it's in earning value. Less than 1 means it's losing value. Okay? X is our input and Y is our output. So what you plug in versus what you get out. All right, so look at this little example on the side right here. Y equals 4 times 1/2 raised to the X. Which one of those pieces is my A value? Look at this form. Which one of those is my A? The 4. Good. That's my y-intercept, right? Which means 1/2 is my B value. I'm going to zoom in right quick. So is 1/2, is that greater than 1 or is that less than 1? It is less than 1. My B is less than 1. So is this a growth or a decay? It's a decay. Okay. This guy right here is what's going to tell me. Okay. So y-intercept is the 4, and this is actually losing half of its value as it keeps going forward. So your next point is at 2. Then the next point is at 1. Then 1/2. Each time it's decreasing. All right. This guy. Y equals 3 times 2 to the power of X. Which one of those is your A value? Your 3. What is your B value? 2. This is a growth or a decay? Growth. Why? Because 2 is bigger than 1. Absolutely. Okay. So this one starts at a y-intercept of 3, and then it's going to actually double its value. So the next point is going to be at 6, and then 12, and then 24. We go with the actual function? Yeah? All right. We're going to look at the 2 different graphs here. We okay? We got that? All right. Here we go. So we have growth and we have decay. Growth, they call it a backwards L. I've also heard it called a J curve because it looks like a J. And then your decay, I think, looks more like the L itself. Okay? So when we have a growth, okay, it's going to be increasing. Okay? Remember, we read graphs from left to right. So as I move across, we are increasing in value, right? Looking at this graph right here, they have graphed y equals 2 raised to the x. What is the y-intercept for this one? What is the y-intercept? Remember, these are my x's, these are my y's. Where is this graph crossing the y-axis? This right here. That is at 0, 1, right? Do you see a 1 in the equation? No, that should be my a value, right? If I write my equation like this, is that technically the exact same thing? Did I change my problem? No, I didn't change it, okay? So that's that invisible math. So there's my y-intercept, and then it's doubling as it's moving forward, okay? Another thing about these graphs, my domain. Domain is your x values, okay? And what's nice is it's always the same thing. Nothing is stopping my graph going left or right, so my domain will always be all real numbers. All right, let's look at decreasing. We good? Yeah. All right, so this one, moving from left to right, Okay, they are decreasing in value. So your y values are getting smaller. That's how I know this is a decay model. Okay, so my y's get down, down, down. Where is the y-intercept for this graph? It's at 0, 1 again. And again, in my equation, I can put a times 1 right there, and I'm not changing it. Okay, and your domain here is going to be all real numbers again. I'm going to do all real numbers. There you go. Okay, there is a symbol. It's a double-lined R. Like that. Yep, same thing. Good question. Okay, so I've touched on the domain. Now when it comes to range, this is the last little information dump for you. Your range is attached to something called an asymptote. An asymptote. I know, fun word. Okay, notice how these curves are like leveling out, right? They don't seem to ever cross the x-axis. Okay, so what it is an asymptote is actually an invisible line that my graph is going to approach but never actually touch or cross. Look at Desmos right here. Ooh, come back. Where'd it go? Come on, thank you. Here we go. I believe this is from the y equals 2 raised to the power of x. Okay. My y-intercept is still 0, 1. My points are doubling in value. But notice as far as I zoom out, does that ever cross the x-axis? It never does, okay? And that's because of this asymptote that exists. There's nothing I can plug in to make my number be a negative number out. Even plugging in negative numbers in my warm-up, all it did was make it a fraction, right? It never changed from positive to negative. It can never happen. So that's this fun thing called an asymptote, okay? And it's always going to be horizontal. We always write it as y equals a number. In the world of asymptotes, there are vertical and slant asymptotes, but you will not be dealing with those when it comes to exponential functions. Okay, so they exist, slant, like a diagonal line. Okay, we're going to focus on just the horizontal ones. Okay. So these lovelies right here, so they've been shifted a little bit, right? Okay, this one's not at 0. Where is this one now? Well, they got bumped up. It's not y equals 0. It's y 2. Yeah, y equals 2. Okay. Is that a growth or a decay, by the way? A growth. Nice. My next one is a decay, and my asymptote has been bumped down to y equals -3. Whoops. Come on. There we go. Like that. Okay. And these affect your range because your range is your y values. Okay. So your asymptote is always y equals a number. Your range will always be y is greater than that number because we're not reflecting in here. So see how it's all sitting on top of that line? So your range, it's almost the exact same thing, but we're going to say greater than 2. Here we're going to say greater than -3, like that. So your range and your asymptote are directly connected to each other. You have a question? What's up? Greater than. Because look at all my y's. Is -4 or -5 on that curve? No, but -2, -1, 0, 1, all the y numbers that are bigger than -3, those are going to be on the curve. Nothing below it. So that's why. Good question.